Hi, we are in chapter 17 and section 17.1. We will be talking about mass moment of inertia. In this case, we will calculate the mass moment of inertia about the y-axis of this volume. So it has the height of 1 feet and it has the curve that describes their boundaries is y squared equals x. And in the top it has a radius of 1 feet. We know the density of the material that composes that volume, and what are the method that we are going to use? The mass moment of inertia of a disk in a, so that will be, see, so it's in y, which is perpendicular to the surface, is 1/2 the mass times the radius, which is the radius of the disk radius. So that's the mass moment of inertia respect to the direction that is perpendicular to the surface of the disk. So I'm going to draw this tiny disk right here. And that is, it has a height of dy, right? And so this is a height dy and has a radius of x. So if the moment of inertia of that disk is y equals 1/2 mass r squared, we can imagine that this disk is a differential of that volume. So we could use this same equation but to say that the Ey will be equals to 1/2. My radius here is not r but x, so I will say x squared, and I have a differential of mass of my whole volume. To find the moment of inertia of this whole volume, I will integrate, right, over the volume, and here over the mass. So this is from here, I'm going to right here. So my mass moment of inertia will be the integral of 1/2 x squared dm. But actually, since I want to integrate in terms of the volume, I'm going to write my differential in terms of volume. As you know, mass is equals to the density times the volume. I will have the area of that tiny little piece. So it will be pi times r squared, and the r is x squared. And the height of this tiny little, this is dy. So instead of doing an integral in three dimensions, because the volume will be a triple integral, I can write it in terms of just one variable, and then I get to have a linear integral, a one-dimension integral, which is much easier. So I will substitute that in here, and I have my borders for y will be from 0 to 1. And I will say 1/2 of x squared rho pi x squared dy. So here I have 1/2. I can get it out of the integral 0 to 1. And actually rho and pi can also go out of the integral because those are constant, rho and y. And I have x to the 4th dy. And in order to be able to integrate my x, and my variable of integration is y, I will substitute it by my equation that gives me that profile. So that will be equals to rho pi over 2, the integral from 0 to 1, and then I see that each x is y squared, so that will give me y to the 8th dy. So finally, that's a very easy integral, right? So Ey will be rho pi over 2 times y to the 9th over 9th, evaluating 0 to 1. And now we just have to plug those numbers that give me rho pi over 2, 1/9. Well, we can write that as rho pi over 18. So if we know now the value of that density, we plug it in here, and we get that y will be rho, which is 5, pi, which is, 3.1459 over 18, and we get that our mass moment of inertia about the y-axis will be 0.873, and the units are very important, which is slug feet square. You can see also the results in the PowerPoint presentation.